Hi guys, we are on our last unit. It's called heat or thermodynamics, and it's about thermal expansion, heat, and calorimetry. So to start, we are going to start talking about temperature and the different scales that you can have, Celsius and Fahrenheit. That's what you'd be familiar with. So temperature is a measure of the warmth or coolness, as you know. Celsius, we've got 0 degrees is freezing, 100 degrees boiling, and 32 degrees is normal body temperature. With Fahrenheit, as you can tell, we have a little formula that links both of them. So if you have a number in Fahrenheit, you'd subtract 32 and times it by 5/9. And if you have a number in Celsius, you would times it by 9/5 and then add 32 to get your Fahrenheit. So you need to know that conversion. Then another temperature scale is Kelvin. You might have seen this on your travels in chemistry. So this is about absolute zero. Absolute zero is the coldest attainable temperature. And as we see down here, 0 on the Kelvin scale is equal to minus 273 Celsius. So the conversion there, Kelvin is Celsius plus 273. You'll see in some of the problems we're doing, you have to find the delta T, the change in temperature. So the change in temperature just gives you a number, and sometimes, no matter if it's in Kelvin or Celsius, they all cancel anyway. We'll see that as we get to those problems. So you don't always need to convert, but I'll show you as we go. So this is how you convert, though, from Celsius to Kelvin. So this problem, you have something in Fahrenheit and you need to convert it to Kelvin. So first of all, you take the Fahrenheit and you use the formula. Fahrenheit is the number minus 32 times 5/9. You get an answer in Celsius. Then you add 273 to get an answer in Kelvin. So let's talk a little bit about thermal expansion. So this is when you can heat up a metal, and most things, when you heat it, they expand. Not every single one. As you see here on the screen, water and plastics, when heated, most materials expand when heated and contract when cooled, but water and plastics are exceptions. So we'll talk about those more as we go. So when we talk about expansion, it can be a one-dimensional thing, which is, for instance, length, a two-dimensional thing, area, or a three-dimensional thing, volume. And there's formulas that go with each one of those. So the length, the area, the volume, and if it's a liquid, we use this little symbol. So this is your beta, and this is an alpha, and they are constants that go with each material. So for this one, the thermal expansion coefficient. Different things expand in different ways, and they have different coefficients, of course. The units on these are 1 over degrees Celsius, or degrees Celsius to the -1. When we start using more complicated equations, it will all make sense, and your 1 over degrees Celsius will cancel with the other units. And so it's you'll be given any of these that you need, and it's showing you here that alpha is linear. It goes with the materials that are going to expand in a line, and the volume, the beta, that's for materials that are liquid, the liquid version. Alrighty, wait now. So the liquid version down here, but it can be the volume if it was a solid piece of aluminum and you were figuring out the volume of aluminum. So the expansion of holes. Let's look at diagram 1 to diagram 2. First, you have something unheated, and if you heat the whole thing up, everything expands out, and the hole is expanded from A to B. So it's obvious, but yet it's not. If you're going to heat up this whole material, everything is going to expand, and the holes expand or contract just as if they were filled with the surrounding materials. Water does a few different weird things, but at 4 degrees, that's when water has the highest density. So we know it's boiling point, we know it's freezing point, but it's the densest at that point. This will never be part of any of your equations, but it's just one of those weird things that water does. So below 4 degrees, as it cools, below it expands because of repulsion between the hydrogen molecules. Alrighty, so volumetric expansion. So let's talk about a liquefied petroleum tank, like the picture here. So we've got that tank and it's 20 degrees. So that's all as well. It's 4,000 meters cubed. That's the volume of the tank. Relies on pressure to contain the liquid petroleum inside. The liquid petroleum expands when heating the tank to 49 degrees. So first you're being asked to find the expansion coefficient, so the beta that goes with the liquefied petroleum. So you use your volume equation, you fill in what you know, and you get your beta. So that is the coefficient that goes with the liquefied petroleum. So problem 2 asks this kind of special thing here now. Calculate the temperature resulting in no headspace, meaning there's no little room left over. Like in a can of Coke or in a bottle of Coke that you can see inside in the plastic bottle, there's some room left at the top. This question is asking you, if you have a steel tank and it's got liquefied petroleum in it, what would be the magic temperature resulting in no headspace? So underneath here, note, you're being asked to find the final temperature when the volume of the liquefied petroleum is equal to the final volume of the steel tank. Once the temperature exceeds this value, the tank will blow up. So a screen ago, you figured out the coefficient with the liquefied petroleum. And from here, we are going to see what we can do. We have first of all, the expansion of the liquefied petroleum. So we have our final, initial, we have all the bits, and we get down this far. That's our final expansion of the liquefied petroleum. We do the steel. We've got all the bits of the volume, we get down this far. You're being asked what's going to happen when the final volume of the steel, the container, is equal to the final volume of the liquefied petroleum. So you have to allow those two to equal. So we let both of those equal, and you get a delta T, a change in temperature of 35 degrees. So if it goes up by 35 degrees, that's when there won't be any headspace and you're going to get yourself in some serious trouble. So 35 is added on to the initial temperature, which was 20. So the final temperature is 55. If we go from 20 to 55 with a delta T of 35, you're not going to have any headspace. The whole thing is going to blow right past that point. Okay, shrink fit. Shrink fit is kind of cool. This is when you want to take two components and fit them together and lock them together. So imagine you have a steel rod and a brass ring, and if you heat up the ring or the rod or both, it depends on what you're going to do, you can maybe slide both of them together, and that's called shrink fit, because when you let the whole thing cool down, they're going to be stuck together, locked together. So this problem is about that. And you're being asked, if you have a brass ring and a steel rod at 10 degrees, and they have different diameters, calculate the temperature when the rings can just fit together. So for them to just fit together, that means that the diameter of the ring is going to be the same as the diameter of the rod. Yes, so that's what you're asked to do. So you could do this in area. So you could do the area of the brass ring. So that's a pi r squared, and then the area of the steel rod. So the brass ring, again, you've got your formula. You fill in all of the parts that you know, and you've got your steel rod, and you fill in all the parts that you know. You're being asked, when can you fit them together? So you have to allow each area to equal each other. So the area of the brass ring equaling the steel rod. So once they both equal, you can work out that the change in temperature would have to be 870 degrees. That's the delta T. So you started at 10 degrees. So therefore, if your initial was 10 and your change is 70, your final must be 880. So you were at 10 degrees, you went up by 870. When your final temperature is 880, those two final areas will equal, and you'll be able to fit the two things together, which is kind of cool. Last slide in this little talk is going to be about the difference in these three items. So I think this visual sums it up the best. So conduction, transfer of heat by direct contact, like touching the pot. Convection is when the heat moves around. So you've got, it could be with clouds and warm air rising, or it could be inside the pot itself from inside the water going from hot to warm. So that's conduction, convection. And then radiation, that's the transfer of energy with the help of electromagnetic waves. So that's the difference in those three items. That's all for now.